David? Yeah, Java. So it's working now, I think.
Hey.
Yes, hello YouTube. It works now. We're going to give a few minutes to those people who left the stream. I'm gonna share that it's working now.
Cool.
Hey, this is working.
Yes, it's working now. I'm going to share that on the social networks because people left, but 1 second. All right, perfect. So thanks everyone for your patience and sorry for the technical issue. So thanks for your time, David. And today we have here my friend Joe. He is from North Wales, and he's an experienced rocket man. He has launched several rockets. He's also a record man, and he will explain that later. Right now, he's starting a new venture. It's a non-profit organization called Open Research Rocketry, and he is going to tell us about this venture and about rockets. And if you have questions, even if the questions are in Spanish, in Galician, or whatever, just left the questions in the chat. I will check the questions, I will translate them, and I will ask him the questions on this stream. So thanks, Joe, for your time, and without further ado, the floor is yours.
Hello, everybody. Thank you ever so much for inviting me to share some of my experiences and talk to you about my crazy ideas with Open Research Rocketry. I thought I'd just start off with a little bit about me. So yes, I'm Joe. I'm also known as Concrete Dog. That's like my personal sort of handle online platforms on Twitter and things like that. I'm a freelancer. I do all kinds of little bits. I work in a few sort of maker spaces. But one thing people sort of know me for a little bit is I write for Hackspace magazine, which is part of the Raspberry Pi press group. Interestingly, if you didn't know, Hackspace magazine, you can get all the issues for free as PDF downloads on the Hackspace site. Typically, I've started a live stream and my phone has exploded with notifications, so that's typical. But I'm known for sort of making lots of different things, but I do a lot of stuff with rocketry. I've done things like I've sat on the UK Rocketry Council, which deal with the sort of safety issues and aspects of UK rocketry. And I've designed and flown numerous kind of rockets and stuff. So this next slide, that's this rocket here, which is a nice sort of nice sized. It's about kind of maybe 1.5 meters tall rocket. It's a high power rocket, so you need some certifications in most countries around the world. You'd need to do a sort of certification flight as part of a rocketry organization to be able to sort of legitimately fly this sort of size and power weight of rocket. But the reason I'm quite proud of this one is that it's completely open source. So the design for that rocket is all published on my personal GitLab repository. But also, not only that, I try to use open source tool chains to make everything, so that hopefully people can, there's a lot of difficulty in getting into rocketry, and I think if we can use open tool chains and open source stuff to help make that more accessible to everybody, then that's a good thing. So I took this other photograph in of this tiny rocket, which I also have here. This is about the smallest rocket I've ever built.
I'm not sure if people can see the cameras.
Okay.
Yes, I think they are working on that, but please, people from YouTube, confirm there is no, you cannot see the cameras.
Okay, so they're just getting the presentation view, is that correct?
Yeah, apparently they are just getting the presentation view.
Okay, so in the slide is the rocket that I've got in my hand at the moment. It's tiny. It's around, I would say, 18 centimeters long, and I designed and built this rocket because I wanted to try and have a go at breaking an altitude record for the smallest motor class of rockets that there are, which are A-impulse class rockets. And I'm very pleased to say that just coming up to 2 years ago, in May, I broke the UK altitude record, which used to stand at 143 meters, but now stands with this very rocket at 214 meters. So it shows you that there's lots of fun to be had in terms of building big, complex, high power stuff, but there's also lots of fun that can be had in you don't need a massive workshop. If you've got a small desk and access to a laptop and some basic sort of tools, there's certainly fun to be had in rocketry. I chucked in there, that's the official sort of entry in the UK Rocketry Association's certification page for that rocket. You can see that I beat the previous record basically by reducing the mass of the rocket massively, and I got it down to its global lift-off weight was 17.99 grams, which included the motor and all the recovery stuff as well. So yeah, this slide is a brilliant piece of open source software called Open Rocket. It's I can see that some people would probably shudder as I say this next bit, but it's a little Java application. But it's a Java app that allows people to design rockets and then simulate them in flight and kind of plot the altitude and the time of flight and the velocity at different points of the flight. It's a really cool bit of open source software, and is reasonably intuitive to use, but there are numerous guides out there, including a few that I've written, and I've got a couple of videos that help people get started with this tool. The brilliant thing about this is that all the solid rocket propellants, which is mainly what I do, so motors that have a solid lump of chemicals that burns and produces hot gases to push the rocket up, all the rocket propellant companies supply data, and therefore this bit of software has profiles for all the motors that you can actually buy in the real world. So you can design a rocket and you can simulate it flying it with a motor that you know that you can purchase perhaps from your vendor or online. So it's a really funky bit of software, and as I say, there's lots of guys there. Maybe after this I can cobble together some links for everybody, or indeed you could check out the Open Research Rocketry website, which has links to most of these bits of information.
Joe, I have one question from YouTube. It's
Fantastic.
from Nacho Cortizo. He's asking if any ideas when we'll get Estes EF certified here in the UK. Oh,
well, I'm not so sure, to be honest, about the Estes. I thought that Estes E and F were were certified, and they are on the HSE list as available to import to the UK. But I just think that they're not kind of perhaps not popular enough. But the Estes E motors sort of had a bad reputation at one point for not performing too well. And sort of not working correctly. So I'm not sure whether the problem is the certification documentation or whether it's just vendors don't have them. And it's weird between sort of D and for E and F motors. I think it's perhaps a little unclear for like model shops to know what the ruling is around mid-power rocketry. But interestingly, what I'm seeing in the UK is more prevalence of E and F rated motors from reloadable companies like Cesaroli, for example. Yeah, so perhaps that's something that you could look into as an alternative, maybe. Hope that answers your question. It's weird. I don't know whether to pause for a comeback or.
Yeah, you have to wait. You have to wait 10 seconds. Yeah, you can go ahead, and if he has more questions, I will let you know again.
Cool. And do keep pinging me questions. I'm not an expert in everything, but do keep interrupting me with questions. That's great. Because I haven't got enough slides to fill massive amounts of time.
No problem. They are asking me whether we can reload the. Because since we have no cameras, can you reload the tab, and so basically exit and come back again and see if that fixes the cameras?
Yeah, I can do that. Yep.
Sorry, YouTube. We will be back soon. Hello, Joe. You're back, right?
I'm back.
No, I don't. And I can open the stream and take a look. Wait a minute.
Hello, Joe.
Hello.
Right, they are. Yeah, we're on YouTube now. All right, we have cameras. Perfect.
Yeah, we have cameras.
So
I'm
again, this is Joe.
I'm better in a dark room, really.
Sorry again for the technical issues. Now you have Joe, and you have some rockets behind him, and also a nice picture of John Coltrane, and also you have a second camera with more rockets. I hope we can make the talk more interesting and interactive now.
Cool.
Back to you.
So yeah, I just put this very poor slide in that sort of the interesting thing I was talking before about. Hang on, my slides have stopped progressing.
Wait. We have to make you the host again.
Yeah, I've lost control of the slide. Yeah.
If you can click in the plus button, you will see a button saying I don't know, hosting.
Oh, hang on. I think it's just come back.
Yeah. You have right.
Yeah.
All right. Yeah. Perfect.
So I was talking about this free open source bit of kit called Open Rocket, which is fantastic. And one of the great things about it as well is that it can you can design parts in it for your rocket, and then it will spew out some things that can be useful in the actual fabrication. If you wanted to scratch build a rocket, it's a very useful tool because it can export, for example, things like it can export a PDF of the fins to give you a template, which you may then open in something else to redraw, but it starts to give you like the kind of pathways where, for example, I use OpenRocket, export PDFs of the fin patterns that I've developed and maybe the other parts, internal parts of the rocket. And then I'll use other open source stuff like Inkscape to tweak those drawings, before perhaps sending them to like a CNC router. And also you can use other software to model different parts of the rocket. So this next slide, I keep clicking my arrow keys to progress slides, but that doesn't work. So just if I've put Open Rocket in the middle of this this slide here, just around it are some of the other kind of open source tools that I use on a regular basis to help kind of make parts for my rockets. So for example, you know, nose cone geometries are quite tricky sort of items to build. I certainly wouldn't like to try and carve one out of, you know, balsa wood or something. I'm not skilled enough for that. But through a combination of knowing what type of nose cone I've designed in Open Rocket and knowing dimensions of it, I can. And there are some great examples of ways that people have built these using things like OpenSCAD, which is like a code-based CAD environment. So somebody has basically written there are lots of script examples out there of scripts that help you generate geometries of nose cones using OpenSCAD. And things like FreeCAD as well can be really useful for that kind of stuff. So 3D printing using open source stuff for nose cones is one technique. Another technique, I'll show it on my phone camera maybe, is 3D printing molds. This little red nose cone is a fiberglass nose cone that I've laid up in fiberglass, but I've used 3D printed molds to help me kind of realize that. So yeah, lots of nice open source CAD stuff. Then things like Inkscape for drawing fins and other parts, which I can then use FreeCAD, for example. I could import those into FreeCAD, set up some tool paths to cut those on I've got a little CNC router at home, or if you've got access to like a makerspace, you could go from Inkscape to a laser cutter to help cut some plywood. But even down to like you know, using things like Cura so that you can publish your files so that people can tweak your settings. And then down to I'm a real love trying to make everything as open source as possible. So even like I try and run my CNC machine off you know, open source things like GRBL or other sort of G-code senders. And of course, for sort of if you're getting into, as I'm slowly getting into, but others in the rocketry community are involved in, if you're building like little electronic payloads, you might use things like KeyCard to help you realize those. And of course, there's lots of stuff that we can do with things like Python and other open source platforms. So I've pressed the wrong button to move my slide again. I'm going to learn that just by the end of this presentation, I think. So open research rocketry is something that I'm currently in the process of setting up. It's going to be, as Shabby said in the introduction, it's going to be a non-profit limited company here in the UK. We've actually put the business side of it, the business setup side of it on hold for the moment because with the current lockdown, there's no high power rocketry sort of ranges open in the UK and stuff. So it seemed to just add complexity at the moment, but we'll get back onto that as soon as things with this virus start to change for the better. But what Open Research Rocketry is going to do, hopefully do numerous things. The first thing, front and center, is it wants to promote an open source approach to rocketry around the world. And it wants to create more sort of interest in open sourcing stuff to do with rocketry. And there's a few sort of reasons for that. So the first line on here is that in amateur rocketry, from model rockets through to great big high power rockets, there's a real prevalence of sharing. If I go to an event and I meet sort of people who fired off far more complex, far more number of rockets than I've ever done in my life, most of them are really, really, really happy to share their experience. They're really excited to tell you the way that they've solved technical problems, you know, and they're really kind of happy to share. but sharing doesn't necessarily mean that something is open source. So by that I mean, you know, I can share the ideas, but I don't really know if I'm allowed to use those ideas, because perhaps I don't know whether you know, they're licensed or whether they're proprietary and stuff like that. So I want to build that culture of sharing, but make it more practical, so that people understand a bit more about open source and how that works, so that people can then really leverage the sharing that happens. And another area around open source and sharing is that a lot of rocketry, a lot of newcomers to rocketry seem to come into rocketry via like academic rocketry teams, which is really cool. Like it's a really great way to get into rocketry. So that might look like at the moment, we're seeing lots of university groups setting up around rocketry who maybe haven't got much experience with rocketry, but because they're an academic rocketry team, they maybe set themselves the goal of taking part in like the America Spaceport Cup, where you build a great big massive rocket and try and fire it to sort of 10,000 feet, which is a huge complex kind of project. But often these academic teams and other teams, to be fair, are in competitions. So sharing is a little bit less prevalent between those teams, because they're in a competitive model against each other. But quite interestingly, they come to the sort of amateur and research rocketry communities for help. So I saw there was a slight sort of issue there of you know, we need to make sure that if we're creating a sharing open source culture around rocketry, that everybody can access that, and that stuff flows kind of from all different teams wherever it can. Open Research Rocketry really wants to promote rocketry, and one of the biggest problems rocketry has is that people just don't know how to get started or how to join in. So we want to do stuff to you know, help address that. And then another really interesting aspect I find in the UK, and I'm not sure what it's like in other parts of the world, I've got some overview of some areas, is that there's no real sort of data collated on amateur and research rocketry. And that's from both, I mean, that perhaps is, if I go to like a local-ish rocketry club in the middle of the UK, they might keep data about what happens at their club, but it's not particularly kind of shared. So it's quite interesting that it's a community that can't necessarily always represent itself, because it's really difficult to be able to say, like, if somebody asked me, like, how many rockets were launched in the UK, how many amateur model or high power rockets were launched in the UK last year, I wouldn't be able to tell them. Which, if people were sort of, I don't know, maybe looking for funding to set up a community project around rocketry, that's a real challenge for them then, that they haven't got that data. But there's also other inconsistencies in the data around rocketry. So the other area is flight data. There are lots of people who are into rocketry, and we fly electronic altimeters in our rockets, but we all use different types. And we all have different kind of, therefore we all have different precision in our data, and there's no kind of central place where that's particularly stored or shared. And that's something that Open Research Rocketry is really interested in trying to develop kind of ways to solve that. And then I've put at the bottom here, clear licensing promotes uptake. Rocketry is full of sharing woes, which brings us back to that open source thing. That there are some great projects online. I won't sort of name names, but there's a couple of fantastic altimeter projects out there that are kind of, the code's been shared, but there's no license on the code, so people don't know if they're allowed to use it, or in what way they're allowed to use it. Like, are they only allowed to use it if it's non-commercial? Can they change the code, for example? So promoting sort of decent open source practice, getting stuff, using as much open source tool chains as possible, and also getting people to license their projects is key, I think. So as such, we've got a bit of a website up and going, and we've got some projects of our own that we're starting to promote. The first one we did was one that I kind of set up to fail. So we had a flight survey that people could self-select to fill in, and tell us about a rocket that they'd flown. So it was a series of questions, and they could fill it in and tell us some of the details about a rocket that they've flown, to see if that was a good way for people to collate data. I kind of knew that it was potentially going to fail, but I kind of wanted to try it anyway, because I thought it was interesting to research whether that could work, and then it might give me some fuel and some argument to say, well, actually what we need in the community is perhaps more of a kind of online hub that hardware maybe connects to, and we can submit our logs more kind of automatically from a sort of shared kind of flight computer platform, for example. And we have we've just released this last week. This is a sort of a first open source hardware project to do with rocketry that we've released, mainly as a kind of test example. I'm not sure it's the most useful project in the world. It's a little electronic match igniter circuit. So it's a circuit board, and when you build it up, it basically switches power to ignite a electronic match. Electronic matches are little wire igniters with a sort of explosive match on the end. If you've ever sort of fired even the smallest model rocket, you've essentially used a type of electronics match. But they get used in more complicated rocketry. For example, if we look at the open source ODR rocket again, this rocket would fly up to apogee, to the top of its flight, and then at the top of its flight, the altimeter inside it would explode, would toggle a pin that would fire an E-match and a small charge, which would blow this rocket section apart, and it would then put out a small parachute. So it would start to descend really quickly, much too quickly than you would want it to hit the ground, but it would be coming down quickly but close to you. The problem is if you put a large rocket up to, say, 3,000-4,000 feet, and you put out a big parachute at the top of the flight at apogee, if there's a slight crosswind, you're going to have an extremely long walk to retrieve your rocket. So what people do is this thing called dual deployment. So at the top, the first deployment is we pop a part of the airframe apart and release a very small parachute, which brings it down very quickly, but not drifting away from you as far. And then we've programmed the altimeter with a predefined return height to explode the second charge to release the main parachute. So that typically might be, I don't know, 300 or 500 feet, a couple of 100 meters. And then we might blow off the nose cone, blows off this rocket, for example, and releases the main parachute, which is much bigger and slows down its descent rate. So this little electronic doohickey is basically a board that you can toggle a GPIO input for a few milliseconds, and it will blow up we shouldn't use terms like blow up. It will ignite an E-match igniter. And it's useful if you wanted to build perhaps a modular flight computer where parts of the system are in different stages of the rocket or different sections of a rocket. But also it's useful perhaps for on-the-ground testing when you set up an area and you test that the rocket will actually physically split apart with the size of charge that you're using, etc. So that's open source. That's on there now. If you don't really understand PCBs and stuff like that, the most simple way to get some would be you can download the files and re-upload them to somewhere like OshPark, and I think they will produce them and send them to you for about £3 UK delivered, which I guess is about €3-4 delivered. Was there a question, Shabby?
Yes. People is asking how can they get involved with ORR?
So there's a couple of ways. They can go and look at www.openresearchrocketry.co.uk and look at what's going on there and get in touch. I'll be putting my email at the end of this selection of slides. You can Also, do a search for Open Research Rocketry, or search for us on GitLab and have a look at the couple of repositories that we've got open there. Yeah, we're really keen to have people contribute, and we're in the process of, it's not fully set up, setting up a Riot chat room for people to do online chat about Open Research Rocketry stuff. So yeah, do hunt us down and get involved.
Thanks, Joe.
Cool. We got next. Okay, so the other thing I love about, so I'm really obsessed with not just, like the first rockets I built were made out of kits, which is a really, really good way to start. Buy yourself an Estes, I don't know, there's loads of beginners Estes kits, and you can buy them and build them and launch them in somewhere like a reasonable sized football field or a park. But I quite quickly got into wanting to build bigger and better, but I'm also really interested in scratch building stuff and making stuff on my own. So it's even gone as far as it's led me down the slippery slope into an addiction to sewing. So I started off making, quite simple parachutes out of bits of ripstop nylon that are just a sort of, semicircle, a hemisphere. But then I got into more complex stuff. There are different types of parachutes with different types of descent characteristics, and whether they're more prone to spinning or doing this and stuff. And so it's led me down some really interesting kind of subject areas. And this slide is my latest sort of obsession is building annular parachutes, which that parachute, when you can see it inflated in the picture in my hand, doesn't look like it has much surface area, but because of the shape of the canopy, which is held in place by the very specific lengths of lines on it, this actually has one of the highest drag coefficients of types of parachute design. Even though it's mainly a hole, it's very hard to sort of believe, and it's very counterintuitive, but it has a really, really high drag coefficient. So but they're quite hard to design. There's some old papers in the public domain by a guy called Kanaka is his name, and they're full of all the designs and the maths for how you design these types of parachutes. So, for example, another repository that we've just made public this week is I put together, and this is my coding skills are pretty poor, so any Pythonistas out there who want to get involved in this repository and make it look better, please do get involved. But I've made just a little simple, terrible GUI, but a little calculator that basically you put in a desired diameter for your annular parachute that you want to design, and the number of gauze, which is the number of separate panels you want it to have, and you click the calculate button and it runs all the maths and chucks out all the design parameters that you need to sit at home at night and sew up your own annular parachute. It's a great Corona lockdown hobby to get into. So yeah, that's the type of sort of stuff that we want to kind of build. We've got more hardware projects, ideas that we'd like to build. We've certainly got more open source rocket designs that I would like to pull onto the repos. I also want to move some of the open source designs that I've done under my own personal sort of GitLab repositories. I want to move those under the Open Research Rocketry banner, but also want other people to contribute if they get into designing their own stuff. I love this photograph. That's a photograph of this ODR rocket again, a couple of thousand, maybe a couple of thousand feet up, maybe 3,000 feet up actually, from last summer. One of the interesting things is when I started sharing that I was doing more high power rocketry, and this was quite a big motivation to setting up Open Research Rocketry, is I started having companies getting in touch and asking me, could you fly this electronic thing that we make on a rocket to this height? And so, for example, the first one was a gentleman whose company makes LoRa nodes that measure particulates in the air for air quality measurement. And he was really interested in stuff between 5,000 and 6,000 feet above ground level. And that's quite an interesting sort of height above ground level, because it's too high for a drone, for a quadcopter or a multicopter. And you could sort of pass a high altitude balloon through there, but a high altitude balloon through there is going to continue and go to up to whatever they go up to, and also is perhaps quite an expensive way to do it, and maybe takes quite a bit of time to do. Whereas rocketry sort of sits in a bit of a niche there, where I could fly a rocket to 4,000 or 5,000 feet for around maybe 40 to 60 UK pounds for the cost of the motor, and I could retrieve it perhaps within 20 minutes, walking to pick it up. And so then we could reload that rocket, and we could do it again and again. They offer that kind of niche that we could quite quickly turn around and fly stuff to this altitude. Is there a question?
Yeah. What kind of propulsion do you use?
Great
Like on this
question.
rocket or on any other rocket? I don't know.
So the smaller rockets, sort of model scale stuff, I use, and most people use, black powder rocket motors, which are the standard sort of. There are a couple of companies that make them, Estes, as I've mentioned before, or there's a German company called Klima that make some of the smaller motors. As you step up in size, you get motors like this, which is a used motor. So that's, for example, the last motor that this rocket in the picture flew on. It's what we call a reloadable system, and it's the main chemical in there is ammonium perchlorate. And these particular ones are made by a company called Cesaroni. There's another company that make them called Aerotech. In the UK, it's illegal. It's not legal for people to make their own rocket propellants. And it's interesting because obviously you can see lots of people on YouTube, for example, sharing recipes to make what they call sugar rocket motors and things. But in the UK, that would be illegal to do, basically because of safety concerns of people boiling up pans of propellant on their kitchen stoves. But that isn't the case in all parts of the world. So you need to check your kind of regional variants on whether that's legal or illegal. And of course, you need to really, if it is legal, that doesn't necessarily mean that it's safe. So you need to check out like good practice in that area. Perhaps I'll talk a little bit more about how these rockets work. These motors work. They have numerous grains inside the plastic case. And then if people weren't doing the more complex thing I spoke about earlier, where you release multiple parachutes, the end of the motor actually has what they call a delay charge that can blow up inside the motor at a specified time, which creates a big volume of hot gas inside the rocket, which pushes apart the airframe and releases the main parachute, which is how the smaller model rockets work. They have a motor that burns, and then the motor runs out, but of course the rocket still coasts upward under its own momentum. As it's coasting upwards inside the motor, it's burning essentially a small fuse. And then after a number of seconds, which you know from the packet of motors, or in the case of the larger motors, you adjust them using a tool, and you can adjust the delay time to suit your rocket and your simulation of your rocket. So after that fuse is burnt through, it burns into this looser charge, which blows the rocket apart and releases the recovery method or the parachute. So yeah, that's a bit about how the motors work. Hope that answers the question. To get back to the picture, yeah, I was getting asked by a lot of companies either wanting to fly things in rockets, either for a sort of science or a research reason, or just because of us kind of company branding, like it's a cool thing to do. So obviously, Open Research Rocketry is going to be a non-profit, and part of the rationale for that is that the type of rocketry I do and the licenses that I hold don't permit me to do commercial rocketry without. Well, no, they permit me to do non-commercial rocketry with insurance. If I went and tried to do commercial rocketry, which I could do, I would instantly need to pay like a really large sum of money to do to an insurer to allow me to fly commercially, and that's a lump of money that I simply don't have at the moment. But also, I quite like the idea that people can come and they can sponsor a flight, fly some electronics, or they can fly some branding on a rocket, and we can use that to kind of help perhaps offset the costs of test flying open source rocket designs. And in fact, before lockdown happened, I was in touch with a company who were like, hey, we'd like to sponsor you to build an airframe, open source it, release the design and test it, and we'll pay for everything. We just want some branding on the side of the rocket and we want to be able to film it, which I think is fantastic, because then if other people can have access to that design and they can, get involved, and they can use a proven design built and flown, but somebody else has paid for that development, then I think that's a win-win. Nobody profits, but everybody kind of gains.
Just related to this thing you're mentioning now, Nacho asks again whether you consider flying rockets as a service, as a viable business service in the UK.
That's a great question again. I am aware that there are a couple of companies that aim to do this commercially. And I wish them every success in the world. I think that's fantastic. I want to see more rocketry, whether it's commercial or non-commercial or open source or not open source. I think I'm not sure. I think momentum would need to build in terms of rocketry at lower levels. I think the arguments about people doing orbital insertion and small satellite launches from the UK are almost kind of a separate argument. I think where it's interesting perhaps is this kind of rocketry as a service for stuff between 5,000 and 20,000, 30,000 feet. I think there's some interesting science that can be carried out in those areas. Whether it's I personally don't feel that it's enough. There's enough market for that commercially at the moment. But I think if you're a company that's for example, aiming to do sort of much bigger orbital insertion satellite launches down the line, but you're flying things in that kind of altitude level at the moment, then perhaps it is a viable commercial activity for you, as it offsets some of your kind of research and development. Just my opinion. Plenty of people would disagree with that. So yeah, and I'm interested in building communities that may indeed be a big part of industry in years to come. But for me, that's the stuff that excites me, is like getting people involved, not so much the commercial aspects. Good question though, again. Okay, what's next on the slides? Oh, sorry, Shabby?
I have another question from Felix. He's asking, well, he's mentioning a problem in Spain, and he says that here in Spain, if you want to launch a rocket, some organizations, what they do is they launch it from airports or really remote areas, and he's asking, how do you handle that in the UK?
Good question. So in the UK, we have an organisation called the UK Rocketry Association, which is similar to things that you may have come across in America or other parts of the world. Like in America, they have the National Association of Rocketry, and there's also the Tripoli organization, which is a sort of mainly in America, but has branches across the world. So our version of that, the UK Rocketry Association, holds the sort of position of maintaining a safety code for rocketry. So within our safety code for rocketry in the UK, there are a group of rules that enable people to set up launch sites for rocketry. So currently in the UK, there are 3 clubs which have sites which are often reasonably remote and quite large farms, usually, or areas of sort of moorland that are expansive and there's not much in them. There are 3 that are currently sort of set up to be okay for people to launch high power stuff up to various heights. But even those have to, on an event by event basis, have to do things like submit a thing called a NOTAM, a notice to airmen, which goes to essentially is a piece of paper that goes to the Civil Air Authority and says, on this day we are applying to launch things up to a ceiling of this height between these hours, blah blah blah. And quite often what they get back is they say that, like, for an entire day or perhaps even for an entire weekend, you could launch stuff up to, say, I don't know, say 5,000 feet, but anything above 5,000 feet and 15,000 feet, they would perhaps need you to coordinate on the day. So somebody would ring up a control tower that's assigned to us, and they would give us a window of time, say 40 minutes, for a single larger project to be launched in. So there are all kinds of protocols and guidance that we follow, and also down to safety codes about how launch systems work, and minimum safety distances, and sizes of recovery areas, dependent on the height and the power of rockets that are going to get flown. So there's quite a lot of kind of infrastructure around these clubs. It gets a bit easier. There are other clubs that do lower power stuff. So there's a couple of clubs set up in the UK that typically fly smaller models with less powerful motors. So anything under rocket motors are assigned a letter which increases along the alphabet as they increase in power. So A being the smallest, up to sort of M class being these huge, great sort of motors. So anything under the letter H can be flown without sort of any certification, but still needs to follow some safety rules. So some of the clubs opt to just do low and mid power because you don't have to do things like notice to airmen particularly. So yeah, I noticed that I don't know masses about it, but there is a Tripoli prefecture in Spain, but I only did a very quick sort of search and had a little look. But it looks like, just on some of the pictures that came up in the search, that they've launched quite big things. But whether they've gone to perhaps a different, perhaps even a different country to launch, I don't know. I was involved in the LibreSpace Foundation. Well, I'm still involved in the LibreSpace Foundation, and they're based. Well, they're a global organisation, but they've got a lot of members based in Greece. And a couple of the members from Greece went and did some certification flights with the Tripoli prefecture in Italy. So I'm aware that can happen, that perhaps people can fly things under different in different countries and under different people's rules. Oh, go on.
No, thanks. No more questions. Thanks.
So how are we doing? What have we got here? Oh, so where open research rocketry, one of the aims with the sort of non-profit aspect of it was, we would really like to actually have some commercial activity within open research rocketry. So, for example, if we come up with a hardware altimeter, we would always share these as open source. That's a given. Everything would be open source. But if, for example, we decided that we wanted to do a run of 500 altimeters and sort out and get them manufactured and then sell those, the way that I hope to set up the organization means that we can do that commercially and we can make a profit on those sales. But the idea is that financially we wouldn't be able to sort of retain a profit. I'm not going to get rich off this. Nobody's going to get rich, but it may provide employment for people. And if there is surplus, so if, for example, we did make something and sell it and make some money and there was some profit, the non-profit aspect is the idea is that we would plough the profits back into activities that help promote and enable rocketry. So, for example, one thing that I'd started doing before lockdown was I was working with a local school that had never done any rocketry, and I was voluntarily working with them to teach them how to kind of build, design and build rockets to take part in. There's a competition in the UK that all schools can enter to design and build and launch a small rocket. And it's a competition, it's quite popular in rocketry circles, where they have to carry an egg payload and they have to do a specific duration of flight. They have to try and hit a specific altitude and not go any higher or lower. And they also have to land, and the egg needs to not have cracked. So it's quite an interesting challenge for a rocketry team. So yeah, we'd started sort of showing some examples locally here in North Wales. There was a rocketry team that wanted to form and wanted to enter that competition. Of course, we put lots and lots of time in and got them a really brilliant group of young people, and they were really working hard. They had worked, I'd shown them how to use the design tools and they're away. But then, of course, the coronavirus has meant that the schools have shut and all rocketry is cancelled. So, but we'll get back to it. We'll get back to it next year. So that's the sort of non-profit aspect. So there will be, I'm sure, some commercial activity. Another area that I haven't really mentioned, and it's not that prevalent on the website, is that there's lots of companies in the UK setting up, trying to do sort of small satellite launches in the UK. I don't think, if people want to take open research rocketry that far, I am more than willing to go that far, but it's certainly not on the roadmap for the next couple of years. But what's interesting in the UK is, and also across Europe, is we're seeing lots of countries perhaps trying to solve various policy or procedural kind of problems with rocketry that they haven't faced because they've never launched rockets from their country before. So, for example, in the UK, I know that a couple of companies, commercial companies, have looked at are looking at water-based recovery because we're an island and because it would actually be easier to do some things out at sea potentially. So there are all kinds of bits of policy that would need developing around that. And open research rocketry perhaps could be a sort of a body in the middle that could do this and publish these bits of research openly, so that we're not wasting resources with multiple sort of companies developing stuff that actually there is no commercial advantage in necessarily, in little silos. And also, there comes a point where it links to, like, kind of, if we're replicating work all the time, it has an impact in terms of, carbon footprint and all that kind of stuff. So that's an area perhaps where open research rocketry might find some funding allocated to do some of that research, hire a couple of researchers, but there may be some profits from that again could offset related rocketry community activity that kind of promotes rocketry. What have we got next? Oh, so back to, so I mentioned earlier that's some of the outputs that open research rocketry itself wants to do, but also we've got loads of, we're starting to collate any open source resources for rocketry on the website. So they don't have to be things that Open Research Rocketry have developed ourselves. It's anything that relates in any way to kind of rocketry that's open source. So I'd love to use this platform to just appeal to you all. If any of you have come across any little tools or any little scripts that do something to do with rocketry, or any bits of hardware, or anything that you think might relate to to rocketry that's open source, do send them in, and we'd love to collate them on our resources page of our website. But also go and check out that. There's a little list of small but well curated list of bits of things to do with rocketry that might help people. And that's kind of all I've got in terms of slides, but I've got loads more time if people want to ask any questions. I've got more props. Over to you lot if you've got any questions.
So while we don't receive any questions, I would like to see some of the rockets, and if you can explain how they work, or which kind of rockets do you have behind you or in the table.
Okay. Cool. Oh, make sure my headphones don't. Hang on. I just untangle my headphones. Sorry about that. That was just
No problem.
untangling my headphones. So, yeah, I suppose I'd like to show off the. There we go. This is the. I don't know, Shabby. Will that be switching on the YouTube thing?
Good question. It has to be done manually, but if David is doing that, they will be seeing the big picture, the camera in the big picture. But just go ahead. If David is hearing us, he will do it.
So this is the tiny rocket that holds the A-Impulse altitude record of the UK. It's tremendously lightweight. People always ask, why did you make it thicker at the top than at the base? And it's a good point, because really that is a waste of drag. But the reason is that you have to fly a certified altimeter, and the smallest one that I could actually purchase was too big for this 13mm tube, but would just fit in this 18mm tube. So I had to kind of design the rocket around the altimeter that I had to fly. One of the ways that I offset and reduce the mass of that rocket was I 3D printed my nose cones rather than using commercial ones. And so it's just 3D printed in PLA, but it's printed in vase mode. So that means it's only got like a single 0.4mm wide layer, making it the thing. It's actually sort of see-through, and you can squash it, but it isn't made out of see-through filament. It's just tremendously thin and lightweight. And then it's been sanded and smoothed. At this scale, you even get into you don't paint them, and you use as little glue as you possibly can because you're so obsessed with getting the weight down. So that's kind of the smallest. This is the open source high power rocket that I built. Actually, let's look at this one first. This is a high power rocket that I built for my level 1 high power certification flight. So it was the rocket that I had to fly, that I designed and built and flew to allow me to fly things that were over H-impulse motors. It's quite a simple build, really. It's a 3D printed nose cone. This is just it's cardboard tubes. It's just like the kind of thing you would get a poster in. It's reasonably tough. You wouldn't want to build anything much more powerful than this in cardboard tubes, but it's certainly strong enough and has survived a few flights. It has plywood fins, and the fin design on this, the fins actually go through the wall of the rocket and they join in to the motor mount inside the rocket. So if I turn it upside down, you can see that. So there's an inner tube there into which the motor is assembled, and that fiberglass ring you can see retains the motor once it's in there. But the fins on this rocket actually go through the outer tube, and inside they actually go all the way through and join onto the outside of the motor tube, which makes it very strong. Because one of the rules in the UK that we have is that your certification flights, you have to, the rocket has to survive sufficiently intact to refly again. So if you break a fin off, then you've kind of you run the risk of failing your certification flight. This rocket's big enough that it flies off a launch rail on a launched tower rather than a little rod. The smaller ones just have a sort of like a sort of straw on them that slips over a thin metal rod that basically keeps them stable until they get up to speed. This one has little kind of buttons which slide into the type of extrusion that sort of 3D printers are built out of, for example, that we build launch rails out of, so that they can have like maybe a 2 or 3 meter launch rail or even bigger. So that was the first high power one that I designed. It's designed to split. It's designed to split at this point in the rocket. So when the charge goes off inside, it breaks apart, and the orange parts stay together, and it would pull a parachute out there. On the this open source one, and this is similar design. Fins are plywood, but have a small coating of fiberglass to make them much tougher. This is made out of a special type of tubing called phenolic tubing, which is sold by it's like an engineering phenolic that rocketry companies sell. This one is meant to do the sort of dual deploying system that we mentioned earlier. So as such, it's got an electronics bay inside it. So when this was rigged for flight, the green section would be bolted and connected to this black section. And if I can, it's hard to do things one-handed. If I take that out, you can see it has a section here, and let's get the light on there. You can see here that there's a big kind of shackle. This would connect to a thick belt that goes into the bottom of the rocket, and it's where a parachute would be connected. And then you can see here, there's a couple of wires into an electric kind of block connector, and a small copper cup here. It's a plumbing part, and that would hold the charge that would be triggered by the altimeter that would blow apart that part of the rocket. This middle section here is basically I'm using a stereo jack socket as a remove before flight kill switch for the power system. So if I pull this out, there's no explosives and it's not armed, but you can hear it perhaps bleeping and starting to initialize the flight computer inside. And then on the other side of this section here inside, there's a similar arrangement as we have at this end, but it would blow off the nose cone here, and it's very hard to see, but it actually uses some small nylon bolts as shear pins So these are strong enough to hold the nose cone in during flight, but when the explosive charge goes off, they're weak enough to be sheared off as the nose cone is released. Because one of the problems you sometimes have with high power stuff is that it's such a violent flight up, it shakes parts of the airframe apart prematurely, and that can cause all kinds of problems.
So now that you've mentioned the flight computer, you're still there? Can you hear me?
Yeah.
So now that you've mentioned the flight computer, I have a few questions on YouTube. What they are wondering, how complex or which kind of flight computer, the software, what do you need? And in particular, they are wondering which kind of telemetry are you gathering, and also whether you have RF communications or you just store data. Can you explain us a bit about the flight computer, the telemetry gathering system, and the electronics inside?
Yes. So there's a huge range of different types, and indeed, it's fair to say that probably most rocketry in the UK, people don't use flight computers at all. They'll use the motor will just eject a charge, and they'll use mechanical means to kind of control the breaking apart of the airframe. But that, and then the next step up is people using. Go on, Jerry. Did you have a question?
Sorry. My bad. No, go ahead.
Okay. Yeah. Then the next stage is people flying reasonably simple altimeters that log usually log barometric pressure and well, by the way, barometric pressure sensors work with, they will log pressure and temperature, and from that extrapolate altitude. The most simple ones of those will, like for example, an off-the-shelf Estes one that you can buy, you'll place it inside the rocket. You have to ensure there's a small vent hole so that the pressure inside the rocket is equalized. And then when you get it back, you pull it out and there's a little LCD that tells you in meters or feet how high your rocket has gone. The next stage of that, above that, is there are altimeters that data log. So they will, data log a barometric pressure sensor, multiple times a second throughout the flight. And then perhaps there are various ways of getting that information back. It might be that you pull an SD card out of them. It might be that you, some of them, you have to plug in a sort of UART connector and stick a USB into a laptop to get it off, but not live telemetry, data logging. Then there are sort of the next stage of that is data logging, but perhaps with GPS, for example, so that you can visualize kind of on a map kind of the flight path and stuff like that. And also things like people might start to, there aren't many commercially available, but people have done lots of experiments where they start to fly IMUs, so they're looking at the motion of the rocket and they can track whether it's kind of rolling in flight and stuff like that. Yeah, and then the other aspect of flight where it becomes a flight computer for me is when it controls some aspects of the flight. So we're back again to altimeters that not only log acceleration, height, blah, 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 but also do something with that information. So, for example, fire a charge at apogee or just after apogee to release a parachute, etc. And one more on the way back down. So that's where they become flight computers for me. Beyond that, there are sort of people do experiments with, for example, trying to stream telemetry. There are people at one point in the UK were quite interested in streaming video rather than just logging video. They were interested in trying to stream video off rockets. So some people have kind of built experimental kind of flight computers that incorporate some of that stuff. What else? The other thing is tracking and recovery. Quite often people have these as separate systems, though. They'll have, because particularly if you're doing explosive sort of deployment charges to fire out parachutes, they're so mission critical that quite often people will have a sort of commercial flight computer that they'll use. Often they'll use two as well, and you can often set them to go off 1 second after the other one, so that you've got redundancy on those things. Certainly that's good practice with larger high power rockets. So sometimes people keep this as a separate system, but then the other issue that rocketeers face is tracking and recovery of your rocket. So if you're in a field with a small model rocket and the model rocket is bright orange and it's got a bright pink parachute and it's a clear day and it's only going up to 300 feet, you stand a very good chance of kind of being able to visually see it and watch it come down and walk to where it is and recover it. If you're sending something ridiculously quickly, close to or exceeding the speed of sound, up to 5,000 feet with some cloud cover, you may, even a crowd of people are perhaps not going to be able to visually track that with their eyes. So people then get into flying tracking systems. That can be anything from the classic sort of approach used to be some sort of RF beacon that would maybe be set to start a broadcast after 5 minutes when it's typically going to be back on the floor. And then, so it's not uncommon at rocketry events to see somebody with a big Yagi antenna trying to sort of triangulate on a lost rocket. That's one approach. The other thing that's become quite interesting of late is if the launch sites have got good cell phone coverage, is using pretty cheap GPS trackers that can send their location via a cell phone service. So I actually fly. I haven't got it in my room. It's in one of my field cases, but I fly these very cheap Eastern GPS trackers that I think are designed for parents to give their children. Let's not get into the ethics of that. But yeah, it contains a SIM card that I know works at the main launch site that I use. And so I can actually text message my rocket if I've lost it. And if it's hitting the cell mass, it'll text me with a Google Maps link that I can open, and it will put me usually within sort of 10 meters of the rocket airframe. And so yeah, but that's some of the sorts of avionics that people fly in the rocket. An area we're interested in open research rocketry is one of the altimeters that we use that isn't one of our projects has this really nice function where it's built around an ESP32 chip, and you interact with it. It chucks out its own SSID and serves its own little website, and you interact with it and set the sort of deployment heights and things over its little website, and you arm it with some codes over the website and stuff like that. And we're quite interested. It's not a public repo yet, but we're just looking around at ideas as to how you could perhaps go to the next level of that and have a flight computer that logs some details about the user inputs some information about their model or their rocket, and the type of rocket, the height, the weight, the type of recovery, blah blah, the motor that it's flying on. It does this job of it logs the flight and it deploys charges and does all the flight computer duties. But then what I think would be interesting if there was a way that could then be logged back to a sort of central website where a user could log in and look at their own data of flight, but perhaps also can share their sort of flight logs with other people. It would be interesting and useful in terms of like competition flying, where we could compare stuff that's flown on the same flight computer, even if they're flown, like one is flown in Spain and one's flown in the UK.
That's exactly the last question that I have on YouTube. They are wondering whether there is this open source or open data central database where you can compare performance across different launches or different rockets. Well, they are suggesting that could be a really good idea, actually.
Yes. Help me build it. In the next few days, I'm going to open a repository that literally just has some ideas written in it about it, and no further than that. But I think it would be a fantastically useful thing to build. And I think there are lots of use cases for it. So, for example, a friend of mine is just starting a doctorate in different types of a type of parachute that they're interested in developing, and he wants to do some flight tests using kind of high power rocketry. And so like there's a great use case, is that if he flew the same sort of networked flight computer, he could get back from a launch event at the end of the day, and just all his data about his descent rates and flight durations and stuff is there on his login. Yeah, I think it's an idea that's got some real potential for individual users. It also could really nicely bring a connection between rocketry groups around the world that isn't there. So like we could run a global competition for, quite small rockets, but if we make a flight computer design that's accessible, and then the data from that is shared on this open data, that could really sort of have interesting nice connections for people around the world joining together, getting involved in competitive rocketry, or just the other one is like, people build a kit rocket, or they're maybe considering buying, not off us, a commercial kit to build. And before they spend their money, they think, oh, I'll maybe check the online repositories to see. I could define a search for, all flights of that type of kit. And then they could see how well it performs with different motors and stuff. It could be a way that it informs people's decision-making about purchases and stuff like that. So, yeah, I think it's a fantastic idea. And it's certainly on the roadmap of open research rocketry to help develop that. So, yeah, definitely keep an eye and do get involved and chip ideas in.
And last question, because it's getting late for everyone, is from Felix, and he wonders which parts of the rockets can be 3D printed. In particular, he's mentioning, let me check the YouTube, he's mentioning the nose cones, the fins, and yeah, some other accessories like motor retainers.
Yeah, that's a really good question. And depending on who you ask that question, you would probably get different answers. When I was on the UK Rocketry Council, in the UK, part of the safety code is that every launch at a launch site has a range safety officer who is supposed to sort of visually inspect your rocket, check that it looks kind of safe, ask you questions about the rocket before it flies. And a lot of the range safety officers were asking, what do we do about 3D printed components? And it's a really tricky area because, I mean, essentially it's a production technique and it's a material question. So I'm not sure I can give you a definitive answer. So I am pretty happy whenever I see a 3D printed nose cone. It seems to me that 3D printing is a great use case. Nose cones are a great use case for 3D printing because they're complicated shapes to sort of make using other methodologies. And a nose cone bears force, you know, from the outside, but it's not particularly bearing much of the thrust from the motor. So I you know, apart from perhaps when you get up to transonic, when you're looking at things going faster than the speed of sound, then obviously 3D printing potentially might not be the correct solution for a nose cone. Motor retainers is an interesting one. Again, it depends slightly on the 3D printed material. So, for example, like PLA, some of the motor burn times would bring PLA close to its glass temperature. So there's a chance that they're going to melt and stop retaining the motor, which obviously is dangerous. It's dangerous in terms of it potentially ejecting the motor. It's dangerous in terms of then your airframe not potentially being able to eject its deployment parachute. So, you know, that there's dangers there. But if you're printing them out of ABS or nylon, for example, that might be different. Fins, that's a really tricky one. I personally don't particularly rate my printing skills good enough to get strong enough fins. And also, it's not just the case of a fin necessarily failing and breaking and causing the rocket to be unstable in flight, which is obviously dangerous. It's the fact of if it's going to flutter, if it's going to bend in flight out of shape, and obviously that might introduce roll, or it might introduce kind of trajectory kind of changes that you don't particularly want. So I don't know, but equally 3D printing, you know, to make aerofoiled shaped fins is very attractive because it's a very difficult shape to realize using other methods. I've used in some rockets like this one, I've used 3D printing to make non-standard size tubes. So like this is actually the first rocket I designed and scratch built, and it's made out of a cardboard tube out of the middle of some Christmas wrapping paper. It flies excellently, and it's been a real useful sort of test rocket. But yeah, it's got a very a non-standard tube size. So I've 3D printed the coupling tube for this rocket. But I'm aware that I made sure that to increase my infill, and I did various tests, kind of pressing them with different weights to see how much they flexed and moved. And also I made sure that my layers were adhered very well. So that, you know, if my bed wasn't leveled properly, perhaps, or there was a bit of a blockage in my nozzle, I might have a couple of layers that were quite loosely kind of put together. So I think it has its place. I think when you start putting plastic 3D printed parts into high power stuff, I think quite rightly, range safety officers should be asking good questions about, is it a load bearing area, and checking out with the designer and the flyer, you know, have you done your homework on how this works? Have you looked at the forces involved, and do you believe this is capable of working?
All right, thank you very much. That was the last question. Thanks for joining us. And if anyone has more questions, here's the email. You can ask him. You can also follow him on Twitter because he has some nice pictures of rockets and of music. And yeah, thank you very much for joining us. And if you enjoyed these kind of talks, we are also a non-profit. We accept donations on our website, industriosa.org. And
everybody stay safe as well. And best of luck in your regions with the coronavirus. Take care.
Thank you very much. Thanks.